Good day, everyone. This is Grace Yagonia together with Nelson Jr. Gonia, and we will be reporting about Unit 2, Roots of Nonlinear Equations. There are 4 topics assigned to us. First is the graphical method. Second is the bisection method. Third is the false position method. And fourth is the incremental searches and determining initial guesses. These topics on roots of equations deals with methods that exploit the fact that a function typically changes sign in the vicinity of a root. These techniques are called bracketing method because 2 initial guesses for the root are required. As the name implies, these guesses must bracket or be on either side of the root. The particular methods described herein employ different strategies to systematically reduce the width of the bracket and hence home in on the correct answer. As a prelude to these techniques, we will briefly discuss graphical methods for depicting functions and their roots. Beyond their utility for providing rough guesses, graphical techniques are also useful for visualizing the properties of the function and the behavior of the various numerical methods. For the first topic, which is the graphical method, the graphical method is a simple method for obtaining an estimate of the root of the equation f of x equals 0. Is to make a plot of the function and observe where it crosses the x-axis. This point, which represents the x value for which f of x equals 0, provides a rough approximation of the root. So in graphical method, we simply compute for the function of x. We plot the result and determine the root which crosses the x-axis. So graphical techniques are of limited practical value because they are not precise, but can be utilized to obtain rough estimates of roots. Graphical interpretations are important tools for understanding the properties of the functions and anticipating the pitfalls of the numerical methods. For the first example, the problem statement is use the graphical approach to determine the drag coefficient C needed for a parachute test of mass m equals 68.1 kilogram to have a velocity of 40 meters per second after free falling for time t equals 10 seconds. Note that the acceleration due to gravity is 9.81 meters per second square. The solution is this problem can be solved by determining the root of the equation using the parameters time, which is equal to 10 seconds, gravity, which is 9.81 meters per second squared, velocity at 40 meters per second, and mass is at 68.1 kilograms. So the function of C equals gravity times mass over the coefficient C times 1 minus e to the negative C over mass times time of minus the velocity. So we substitute the values on the function of C. We arrive at 9.81 times 68.1 over C times 1 minus e to the negative 0.146843 times C minus 40. Here we have the table for the C and the function of C. We have the function of C ranging from 4 to 20. And we computed for the function of C using Excel. So these are the results for the function of C. And we have plotted for the result. And in this graph, we can see that the change in sign is between 12 and 16. And through visual inspection of the plot, we have a rough estimate of the root, which is equal to 14.75. With C equals 14.75, we then substitute this value to the function of C, and we arrive at the result of the function of C equals 0.1, which this result is close to 0. To check for this value, we substitute this to the velocity formula for the velocity. Velocity equals gravity times mass over the coefficient C times 1 minus e to the negative C over m times t. So the velocity is equal to 40.1. So the result is close to the desired fall velocity, which is 40 meters per second. For this illustration, this shows a number of general ways that a root may occur in an interval prescribed by a lower bound x sub L and an upper bound x sub U. So here we have 4 different figures showing different roots. So in A, this shows that there are no roots since it does not cross the x-axis, and it has a positive sign. The 2 points both have the positive sign. In B, there is one root that crosses the x-axis, and there are 2 points that have different signs, positive and negative. And in C, there are 2 roots that crosses the x-axis, and it has the same, that there are 2 points that are both positive. In D, we have different signs, and there are 3 roots that crosses the x-axis. Next is the illustration of some exceptions to the general cases depicted. In A, the multiple root that occurs when the function is tangential to the x-axis. For this case, although the endpoints are of opposite signs, there are an even number of axis intersections for the interval. In B, there is a discontinuous function where endpoints of opposite sign bracket an even number of roots. Special strategies are required for determining the roots for these cases. For the second example, the problem statement is computer graphics can expedite and improve your efforts to locate roots of equations. The function f of x equals sine 10x plus cosine 3x has several roots over the range x equals 0 to x equals 5. Use computer graphics to gain insight into the behavior of this function. So we use GNU Octave and we use this command. Then we arrive at this graph of sine of the function of x equals sine 10x plus cosine 3x. The range is from 0 to 5. So this graph permits the analyst to determine that two distinct roots exist between 4.2 and 4.3. So in here, we zoom in between in the range between 4 and 5. So there's a root between 4 to 4.5. So in this graph, we see the range between 4.2 and 4.3. So we can see that there are two roots that crosses the x-axis.
Good day, everyone. This is Engineer Nelson John Begonia, and a graduate of a licensed civil engineer and a graduate of Central Mindanao University. So today I will be discussing to you section 2 of the nonlinear equations, which is the bisection method. So bisection method, alternatively called binary chopping, interval halving, or Bolzano's method, is one type of incremental search method in which the interval is always divided in half. If a function changes sign over an interval, the function value at the midpoint is evaluated. The location of the root is then determined as lying at the midpoint of the subinterval within which the sign change occurs. The process is repeated to obtain refined estimates. So this is the algorithm or the step-by-step process for the calculation using the bisection method. So first, we shall choose the lower values of x as x sub L and the upper value as x sub U for the roots such that the function changes sign over the interval. This can be checked by ensuring that the function of x sub L times the function of x sub U is less than 0. So we shall, for the step 1, we shall guess or assume values, lower and upper values of our x. So the next step is an estimate of the root x sub r is determined by x sub r is equal to x sub L plus x sub U over 2. So by the name itself, bisection or halving or yes, halving. So we shall divide by 2 our values of x's for that x, which is the lower value of x and the upper value of x. So next step is to make the following evaluations to determine in which subinterval the root lies. So first, we shall check by multiplying if the function of x sub L times function of x sub R is less than 0. So the root lies in the lower subinterval. Therefore, set x sub U is equal to x sub R and return and go back to step number 2. The second case is that if the x sub L times the function of x sub R or the function of x sub L times the function of x sub R is greater than 0, it means that the root lies in the upper subinterval. Therefore, the new x sub L now is x sub R and return again to step number 2. And the third case, if the function of x sub L times the function of x sub R is equal to 0, the root equals x sub R. So the root now is equal to x sub R. And the computation will terminate. So having an example or making the example for the bisection method, we will just use the example number 1 from graphical method. So the first step is to guess 2 values of the unknown. So from figure 1, we can see that the function changes sign between values of 12 and 6. So x sub 12 now will be our x sub L and x sub U is 16. So in our first iteration, we can get our x sub R is equal to 12 plus 16 divided by 2 is equal to 14. So the true percent relative error now or the E sub T is equal to 5.3%. Then we shall compute the product of the function value at the lower bound and at the midpoint. So we get function of 12 times the function of 14 is equal to 9.85. So function of 12 and function of 14, we can get it here. The function of 12 is 61139 The function of 14 is 1.611. So if we multiply these two values, we can get 9.85. So 9.85 is greater than 0. Therefore, no sign change between lower bound and midpoint. So we continue with our second iteration. So in our first iteration, we got our new sub x sub r equal to 14. So the second iteration, x sub r will now become 14 plus 16 divided by 2, which is equals to 15. And the 2% error, or the sigma t sub t, is equal to 1.3%. So function of 14 times the function of 15, we get negative 0.619. Hence, the product of these two functions is less than 0. Therefore, we can say that the root is between 14 and 15. So continue with the third iteration. We can refine more and to get the nearest value of our root. So x sub r now will become 14 plus 15 divided by 2 is equal to 14.5. And the percent relative error now, or sigma sub t, is equal to 2.0%. So multiplying the functions of these two x's, we can get 0.957. So under the bisection method, we shall also get the termination criteria and the error estimates. We ended example 3 with the statement that the method could be continued to obtain a refined estimate of the root. We must now develop an objective criterion for deciding when to terminate the method. So in order to terminate the method, shall find a way using these error estimates to terminate the method, or when we will stop the iteration. An initial suggestion might be to end the calculation when the true error falls below some pre-specified level. We require an error estimate that is not contingent or foreknowledge of the root. An approximate percent relative error, or sigma sub a, can be calculated. So, which is sigma sub a is equal to x sub r, the new x sub r minus the old x sub r, divided the new x sub r, the absolute values for that, times 100%, where the new x sub r is the root for the present iteration, and the old x sub r is the root from the previous iteration. The absolute value is used because we are usually concerned with the magnitude of sigma sub a rather with its sign. So when sigma sub a becomes less than a pre-specified stopping criterion, sigma sub s, the computation is terminated. So We have also example 4. So we just continue the example 3. Wherein continue the example 3 until the approximate error falls below a stopping criterion of sigma sub s, which is 0.5%. Then we compute the errors. So here our criteria, or our stopping criterion is sigma sub s, which is 0.5%. So our objective is that we can get, at least we can get sigma sub a, or the actual error near to this 0.5%. So the results of the first two iterations, for example 3, were 14 and 15. Substituting these values into equation 1 yields sigma sub a is equal to 6.667%. Recall that the 2% relative error for the root estimate of 15 was 1.3%. Therefore, sigma sub a is greater than sigma sub t. This behavior is manifested for other iterations. Also, on the table below, as you can see, on the 6th iteration, we derived a sigma sub a for the actual error as 0.422, wherein 0.422 is near to 0.5%, which is the stopping criterion. So for this bisection method, one objective is to apply the method using GNU Octave. So we have come up with a GNU Octave command or program using example number 1. So as you can see, we got at, at, at the bottom portion of the command window, we get the x sub r, or xr, equal to 14.8011, which is also the same with that our example, and a stopping e sub s, or es, which is equal to 0.001%, and ea, which is equal to 0.0008%. So this is the result of the GNU Octave command or program. So as you can see, we got a value of x sub u, or xu, which is 14.8011. Then, so this is the graph for that example. So as you can see, we have the y-axis is the velocity of the parachuting for the parachuter. So, and the x-axis is the drag coefficient. So as you can see, for the velocity equals to 40, or the given velocity, our graph cross that line somewhere between 14 and 16. So we zoom in this one until we get boundaries of because as you can see at the bottom, our boundary now, or the x-axis now, is around 14.801, and between 14.801 and 14.802. So as you can see, the line touches the 40 boundary mark or the 40 mark at around 14.801. So thus, after 6 iterations, sigma sub A finally falls below 0.5%, which is the value of sigma sub S, or this stopping criterion. And the computation can now be terminated. So that result was summarized at the table shown a while ago. Although the approximate error does not provide an exact estimate of the true error, the figure suggests that sigma sub A captures the general downward trend of sigma sub T. In addition, the plot exhibits the extremely attractive characteristic that E sub A is always greater than E sub T. Thus, when sigma sub A falls below sigma sub S, the computation could be terminated with confidence that the root is known to be at least as accurate as the pre-specified acceptable level. It can be demonstrated that sigma sub A will always be greater than sigma sub T for the bisection method. Then XR is equal to X sub L plus X sub U over 2. We know that the true root lies somewhere within an interval of X sub U minus X sub L over 2, or the delta X over 2. So with that equation, then can be substituted to equation 1. So we can get sigma sub A, which is the absolute value of X sub U minus X sub L divided by X sub U plus X sub L times 100%. This is now our equation number 2. This equation yields identical results to equation 1 for bisection. In addition, it allows us to calculate an error estimate on the basis of our initial guesses, that is, on our first iteration. Another benefit of the bisection method is that the number of iterations required to attain an absolute error can be computed a priori, that is, before starting the iterations. This can be seen by recognizing that before starting the technique, the absolute error is E sub A raised to 0 is equal to X sub U raised to 0 minus X sub L raised to 0, or equal to delta X raised to 0. So the superscript 0 indicates that this is our first iteration, or the start of our iteration. So after the first iteration, the error will now becomes A sub A raised to 1. So is equal to delta X raised to 0 divided by 2. So since it's already after the first iteration, so the superscript of the E sub A is already 1, but delta X is always raised to 0. And for the succeeding iterations, we can get E sub A raised to N is equal to delta X raised to 0 divided by 2 raised to N, wherein N is the number of iterations number of iterations. So E sub AD is the desired error. This equation can be solved for n is equal to the logarithmic of delta x raised to 0 divided by EAD over logarithmic of 2 is equal to the logarithmic of delta x raised to 0 divided by E sub AD. So that is how we can get the errors, the absolute error. So that is for section 2 bisection method.
The third method is the false position method. False position is an alternative based on a graphical insight. A shortcoming of the bisection method is that in dividing the internal interval from x sub L to xu into equal halves, no account is taken of the magnitudes of function of xl and function of xu. For example, if the function of xl is much closer to 0 than function of xu, it is likely that the root is closer to xl than to xu as shown in the figure. An alternative method that exploits this graphical insight is to join the function of xl and the function of xu by a straight line. And the intersection of this line with the x-axis represents an improved estimate of the root. The fact that the replacement of the curve by a straight line gives a false position of the root is the origin of the name method of false position, or in Latin, regula falsi. It is also called the linear interpolation method. The intersection of the straight line with the x-axis can be estimated as function of xl over xr minus xl equals function of xu over xr minus xu. So now we derive the formula for the false position method. And first, we cross multiply the equation to yield function of xl times xr minus xu equals function of xu times xr minus xl. We collect terms and rearrange xr times function of xl minus function of xu equals xu times function of xl minus xl times function of xu. Then divide by the function of xl minus the function of xu. xr then equals to xu times the function of xl minus xl times the function of xu over function of xl minus function of xu. It can be put in an alternative form by expanding it. xr equals xu function times function of xl over the function of xl minus the function of xu minus xl times the function of xu over function of xl minus the function of xu. By adding and subtracting xu on the right-hand side, xr equals xu plus xu times the function of xl over the function of xl minus function of xu minus xu minus x1 xl function of xu over the function of xl minus the function of xu. Collecting terms yields xr equals xu plus xu times the function of xu over the function of xl minus function of xu minus xl times the function of xu over function of xl minus the function of xu. Or we have the xr equals xu minus the function of xu times xl minus xu over function of xl minus function of xu. So this now is the false position formula. The value of xr computed then replaces whichever of the two initial guesses, xl or xu, yields a function value with the same sign as the function of xr. In this way, the values of xl and xu always bracket the true root. The process is repeated until the root is estimated adequately. For example 5, the problem is use the false position method to determine the root of the same equation investigated in example 1. Solution. As in example 3, initiate the computation with guesses of xl equals 12 and xu equals 16. So here in the table is shown is the values of x and the computed function of x. So between 12 and 16 is the change of sign. So we use this for the first iteration. Using the formula of the false position, xr equals xu minus function of xu times xl minus xu over the function of xl minus the function of xu. So the given are xl equals 12, xu equals 16. So from the table, we have function of xl for 12 is 6.1139. The function of xu, which is 16, equals negative 2.2303. xr was 16 minus function of xu, which is negative 2.2303 times 12 minus 16 over 6.1139 minus negative 2.2303. So that XR is equal to 14.9309 with relative error of 0.88%. The product of the function of XL and function of XR is equal to 6.1139 times the function of XR, which is equal to negative 0.2515. The product is now equal to negative 1.5376. For the relative error, have computed using the true root, which is 14.8011. The relative error equals 14.8011 minus the XR, which is 14.9309 over the true root 14.8011, which is equal to 0.88%. So with the product of the function of XL and the function of XR, we can conclude that the root lies in the first subinterval and XR becomes the upper limit. The XR, which is equal to 14.9309, becomes the upper limit since it has the same sign since it has the same sign, it will replace the upper limit for the next iteration. So second iteration, XL is still 12. XU is now 14.9309. So the function of XL equals 6.1139 and the function of XU is equal to negative 0.2515. XR equals 14.9309 minus the function of XU, negative 0.2515 times 12 minus 14.9309 over 6.1139 minus 0.2515. XR equals 14.8151. Which has true and approximate relative errors of 0.09 and 0.78%. So in the table is the values of X and the function of X. So we have added 14.8151 And the function of XR is negative 0.0272. So the product of the function of XL and the function of XR equals 6.1139 times negative 0.0272 equals 0.1663. Additional iterations can be performed to refine the estimates of the roots. The figure shows the comparison of the relative errors of the bisection and the false position methods. The error for false position decreases much faster than for bisection because of the more efficient scheme for root location in the false position method. One of the initial guesses may stay fixed throughout the computation as the other guess converges on the root. For such cases, the interval does not shrink but rather approaches a constant value. The pitfalls of the false position method is shown in example 6. Problem statement is use bisection and false position to locate the root of the function of x equals x to the 10th power minus 1 between the values of x equals 0 and 1.3. So for the solution, using bisection, the results can be summarized as follows. So these are the 5 iterations. First, we have 0 and 1.3. Then we have the XR of 0.65. And then the function of XR equals negative 0.987. The error, approximate error is approximate error is 100%, and the relative error is 35%. For the second iteration, the XL is now 0.65. XU is still 1.3. The XR is 0.975 and the function of XR is negative 0.224. The approximate error decreased to 33.3 And the true error, a relative error is 2.5. For the third iteration, the XL is 0.975 and XU is 1.3. XR equals 1.1375 and the function of XR is 2.627. The approximate error is 14.3 and the relative error is 13.8. For the fourth iteration, XL is 0.975, XU is now 1.1375. XR equals 1.05625 and the function of XR equals 0.728. Approximate error is now 7.7 and the relative error is 5.6. For the fifth iteration, XL is 0.975, XU is 1.05625. XR is 1.015625 and the function of XR is 0.168. The approximate error is 4 and the relative error is now 1.6. So after the 5 iterations, the true error is reduced to less than 2%. The true value of the root is 1. So next is the solution by using the false position method. The first iteration, XL equals 0, XU is 1.3, XR is 0.09430, and the function of XR is -1. The second iteration, XL is equal to 0.09430. The XU is 1.3. XR is equal to 0.18176 and the function of XR is -1. For the third iteration, XL is 0.18176, XU is still 1.3. XR is 0.26287 and the function of XR is -1. For the fourth iteration, XL is 0.26287, XU still 1.3. XR is 0.133811. Function of XR is -1. The approximate error is 22.3 and the true error is 66.2. For the fifth iteration, XL is 0.33811. XU is still 1.3. XR equals 0.40788. And the function of XR is -1. approximate error is 17.1 and the true error is 59.2. After the 5 iterations, the true error has only been reduced to about 59% from 90.6%. In addition, note that the approximate error is less than the true error. Thus, the approximate error is misleading. Although a method such as false position is often superior to bisection, there are invariably cases that violate this general conclusion. The example also illustrates a major weakness of the false position method, which is its one-sidedness. The figure shows the plot of function of x equals to x to the 10th power minus 1. This illustrates the slow convergence of the false position method. Next is the solving of the false position method using the GNU Octave command for example 1. This is the command used. This is the result. And the graph after the execution of the command, graph 1 and graph 2.
Now, section 4, which is the incremental searches and determining initial guesses. Another option is to incorporate an incremental search at the beginning of the computer program. This consists of starting at one end of the region of interest and then making function evaluations at small increments across the region. When the function changes sign, it is assumed that a root falls within the increment. The x values at the beginning and the end of the increment can then serve as the initial guesses for one of the bracketing techniques described in this chapter. A potential problem with an incremental search is the choice of the increment length. If the length is too small, the search can be very time-consuming. On the other hand, if the length is too great, there is a possibility that closely spaced routes might be missed. Although such modifications or the employment of a very fine increment can alleviate the problem, it should be clear that brute force methods such as incremental search are not foolproof. You would be wise to supplement such automatic techniques with any other information that provides insight into the location of the roots. Such information can be found in plotting and in understanding the physical problem from which the equation originated. So these are the cases where roots could be missed because the increment length of the search procedure is too large. Note that the last root on the right is multiple and would be missed regardless of increment length. So problem statement. Solve example one using incremental search method. So solution. So mm, using incremental searches, uh, we will guess where where are where is the root lies. So we will assume two numbers or 2 points wherein the root possibly lies. For example, so for this one, so we will choose 14 and 15. Then we will have a 8.1 increment. So like this one, 14, 14.1, 14.2, and so on until it reaches 15. Then we solve each function of x. So using softwares, especially Excel, this could be done easily. Then after solving the function of x, um, as we can see, as you can see, as you can see that at points or areas wherein um, the function of x will change sign, like in this one here, in the first column or the first increment, or in 0.1 increments. Um, the function of x change sign at the point of 14.9. So we can say that the root is possibly located between 14.8 and 14.9. So again, we will have another increment. So from point 1, we will have a 0.01 of increment. So we can have 14.8, then 14.81, 0.82, 83, 84, until it reaches 14.9. And then again, we will solve for its function of x. So again, using Excel, it will be very easy to solve the function of x's. So in our example, at the uh, when the increment is at 14.81 or the value is at 14.81, the function of x is already negative, or there is a change of sign. So we can say that the root is probably or probably lies between 14.8 and 14.81. So therefore, we will have another set of finer increment, which is 0.001. So from 14.8, we will now have 14.801, 0.802, 803, 804, and so on and so forth until it reaches 14.81. So again, we will solve for the function of x for each increment. So on the table, using Microsoft Excel or sheets, Google Sheets, we can derive, or as you can see at 14.802, the function of x, again, change sign or got a negative result. So therefore, we can say that our root lies between 14.801 and 14.802. So therefore, or it's safe to say that the root is 14.801 since the function of x is still at positive. So you can still, if you want, we can continue to have another or finer increments until you are satisfied that the root, or until such time that you can get the exact root. So in this one, we are just bound, or we just our objective is just to get the root with at least 3 decimal places. That's why we just stop at 3 set of increments. So now the root is 14.801. So I think that is for the incremental searches and determining initial guesses. So for this one, incremental searches is just very easy to perform, and also it is easy to solve. We'll just have a set of increments until such time that we can get the exact root. So, and that will be all for this chapter or topic for the roots of nonlinear equations. And once again, in behalf of Engineer Grace Yagonia, this is Engineer Nelson Yagonia. Thank you all. Thanking you all guys for your time and for listening to our topic. Thank you, and God bless us all.